All right, good morning, you guys. Today we are doing quiz prep. So use a calculator for the problems below. Round all calculations to the nearest 10,000, so 4 decimal spots. All right, so first up, find the percent of a standard normal model in each region. It may help to sketch a visual. Okay, so we see our fancy absolute value bars. We know that that reads as magnitude. Right? Magnitude is simply the distance from the mean. So we're looking for the distance from the mean is greater than 1.6. So let's sketch this out. Let me write those words too. So distance from the mean is going to be greater than 1.6. Okay, so if I sketch it out, here's my normal curve, here is my mean, here's about where my z-score would be 1.6, so 1.6 standard deviations above the mean, and then here would be the below. So 1.6 standard deviations below the mean. And we're looking, where is the distance from the mean greater than 1.6? So if I picture myself standing at 0, right, z-score of 0, where the mean is, and I move away from it, my distance is getting greater as I move away from it. So if I want to be greater than 1.6, I'm over in these tails. Okay, so now I'm going to go use my normal CDF. I'm using it with the z-scores. So over here, negative infinity to positive infinity. So what's my placeholder for the infinities? When I'm using z-scores, I usually make it the 99s. So I'm going to say that this is negative 99, this is positive 99. I know that the area here will be the same as the area here. So if I solve for one, I can just double it to get both of them. So I'm going to type in normal CDF, negative 99 to negative 1.6. Okay, mean is 0, standard deviation of 1 when I'm dealing with z-scores. So when I type that in, I'm going to get 0.0548. So over here, 0.0548, here, 0.0548. So I need to double it and then make it a percentage, so 10.96%. Okay. Find the z-score or z-scores that correspond to the middle 66%. So let me draw out my normal curve. Here we go. Middle 66, well, it's just shade an estimated portion, so we'll say that's 66%. I'm trying to find the markers here and here in terms of z-scores. So I know that this is the middle 66%. I have 34% left over here, and I know that these two regions have to match. So if I take 34, split it two ways, I have 17% here and 17% here. I know that the z-scores that go here and here, they're going to be opposites because they have the same magnitude, distance from the mean. So now, since I'm solving for a z-score, I use inverse norm. Okay, right here, the proportion below or the area below is 0.17. Mean, standard deviation, just like that. Okay, it's going to pump out for me a z-score of negative 0.9542. So that would be this one, and here would be its positive counterpart. So, and positive 0.9542. Okay, slide it up. All right, find the missing parameter, the mean or the standard deviation. So here in this one, we are given our standard deviation. We're given the proportion that falls above this observation. So I'll write x next to that. We want the mean. So again, x, we know that that's 215. Let me just emphasize that. Let's visualize it. Here is my normal curve. Here's where my mean should be that I do not know. I know that at an x value of 215, 17.7% falls in this region. Okay, I know that to find my z-score, I always have to know the proportion below. So if I take 100%, subtract 17.7%, here we go, 82.3%. So next, I want to find the z-score. So to find the z-score, I use inverse norm. Okay, proportion below, that area below is 0.823. Mean, standard deviation, 0 and 1. Okay, that's going to give me a z-score of about 0.9269. Okay, so I essentially had everything that I needed except for the z-score. So I had to build off that area that's given, right? Gave it to me as a percent, right? So I found the proportion that's above. I needed to make it the below and make it a decimal. Okay, so now I can go to my z-score formula or my observation formula. My preference is using the observation formula. So x equals the mean plus the z-score times the standard deviation. So 215 is equal to the mean plus the z-score, 0.9269, times the standard deviation of 11.6. Okay, now it's an algebra problem. 215 equals the mean plus the product here is 10.752. Okay, take that 10.752 away from each side. And we end up with a mean that's about 204.248. And there we go. Okay, next up, let me slide up here. A Cornell University researcher measured the mouth volumes of 31 men and 30 women. She found a mean of 66 cubic centimeters for men, standard deviation is 17 cubic centimeters, and a mean of 54 cubic centimeters for women. Okay, standard deviation is 14.5. Okay, so we have our means and we have our standard deviations. The man with the largest mouth had a mouth volume of 111.2 cubic centimeters, and the woman with the largest mouth had a mouth volume of 95.8 cubic centimeters. Assume the mouth volumes are approximately normal. Which gender has the most extraordinarily large mouth? All right, so we're looking at the men and we're looking at the women. Okay, so next to each one I wrote normal and I wrote the mean with its standard deviation. So we're told that the man, the observation for the man was 111.2, and for the woman it was 95.8. Okay, so let's find their z-scores. So for the men, we're taking that observation minus the mean over the standard deviation. So that's getting us a z-score of about 2.6588. Okay, for the ladies, z equals 95.8 minus 54 over 14.5. So we get 2.8828. All right, so here we are trying to look at two different distributions, men and women, strip away their units, compare them on the same scale by looking at them in terms of z-scores. So we see that here the woman has a larger z-score than the man, which would put her in a higher percentile. So we're going to say that the woman has the more extraordinary mouth, because that larger magnitude would result in a larger percentile. Okay, we know that it's deeper in that upper tail region, which means it's more unusual, it's more rare, right? If I actually went ahead and I calculated how many women have a larger mouth value, I would find that it's only 0.2%. So it's very, very, very unusual. Okay, next up, 5. Suppose the heights of kindergarten children can be described by a normal model with a mean of 38.2 inches and a standard deviation of 1.8 inches. All right, so first we're going to summarize. Okay, distribution is normal. Here is our mean. Here is our standard deviation. Okay, what percent of kindergartners are between 37 and 41 inches tall? How amazing. I actually don't have to use my z-score process anymore. I know how to use the raw data. So I can go straight to normal CDF, lower boundary, upper boundary, mean, standard deviation. So you can still convert to the z-scores, but I'm telling you now that it's an unnecessary extra step. We have shortcuts, and who doesn't love shortcuts? So here we're at about 68.76%. Okay, at least how tall are the biggest 10% of kindergartners? Okay, let's visualize. So here's the biggest 10% right here, which means that that marker here would be the smallest 90 over here. So I'm going to use inverse norm. And same thing, I can use my raw data now. Excellent, beautiful shortcut. I do not have to convert to z-scores, not anymore. So here I'm entering inverse norm. Here is the proportion below, the 0.9, that's the area below, the proportion below. And then the mean, 38.2, and the standard deviation of 1.8. So when I plug that in, that's going to produce the actual observation. So it's going to produce for me about 40.5068 inches. Okay, so many shortcuts now, so exciting. All right, let's flip it over or turn to the second sheet. And here we go. All right, according to the wildlife biologists at the Department of Fish and Wildlife, the length of adult largemouth bass can be described by a normal model. They collect data from fishermen, finding that 22% of the largemouth bass caught were thrown back because they were below the 15-inch minimum, and only 6% were longer than 23 inches. What mean and standard deviation should define the model? Okay, so this is that several-step process. First up, I'm going to look at the two separate normal curves. Okay, we're told two separate statements. So here, 22%, they're thrown back. They were too small, below the 15-inch minimum. So let's say I draw that visual right here. X is 15, and here's that lower 22%. Okay, we also know that 6% were longer than 23 inches, so 6% about like that. And that is an X value of 23 inches. Okay, whenever I know the above, I always have to convert to the below, so 94% right there. All right, so I need to find Z. I need to find my Z-score for both. So here I'm using inverse norm, 0.2201, and that's going to get me a Z-score of about negative 0.7722. I'm going 4 decimal spots, trying to be precise. Okay, over here, I have inverse norm, 0.9401, and I get Z is about 1.5548. Okay, next step, I'm going to take it to my normal curve, put both of those markers on the same normal curve. So over here, x is 15, the z value, negative 0.7722. Okay, over here somewhere, x equals 23, z is about 1.5548. Beautiful. Okay, I got to get my standard deviation first. So my standard deviation, here I'm looking up top, the difference between the two observations. The order doesn't matter because once I put absolute value bars around it, it forces it positive. So if I do 15 minus 23, when I put bars around it, it's going to read as 8. Okay, and then beneath it, I'm looking at the difference between the z-scores, tells me how many standard deviations they are apart. So negative 0.7722 minus 1.5548. Okay, but in my bars, it's going to become 2.327. So I have 8 divided by 2.327, which will get me about 3.4379 inches. Okay, so I have my standard deviation, and now I need my mean. So x equals the mean plus the z-score times the standard deviation. So I know that I can build off here or here. I'm going to build off the first one. It's what I typically do. So 15 equals the mean plus the z-score, negative 0.7722. Standard deviation, I just solved for 3.4379. Okay, and again, it's just an algebra problem from this point on. So 15 equals the mean minus 2.6547. And then I just have to add the 2.6547 to the other side. So my mean is about 17.6547 inches. All right, so the largemouth bass have a mean of 17.6547 inches with a standard deviation of 3.4379 inches. Okay, there's several more of these that you guys can practice in older warm-ups if you want to go back and have more practice. I think I also have one in our challenge. All right, moving on up. At fast food restaurants, the lids for drink cups are made with a small amount of flexibility, so they can be stretched across the mouth of the cup and then snugly secured. When lids are too small or too large, customers can get frustrated, especially if they end up spilling their drinks. At one restaurant, large drink cups require lids with a diameter of between 3.95, so it's saying, well, that's the minimum, and 4.05, which would be the maximum inches. The restaurant's lid supplier claims that the diameter of large lids follows a normal distribution with a mean of 3.95 inches and a standard deviation of 0.02 inches. The supplier is considering 2 changes to reduce the percent of its large cup lids that are too small to 1%. One way is to adjust the mean diameter of its lids. Another is to alter the production process to decrease the standard deviation of the lid diameter. So in A, if the standard deviation remains at 0.02 inches, at what value should the supplier set the mean diameter so only 1% are too small to fit? Okay, so let's visualize what's going on. So first up, we know that normal distribution, here's our mean, and our standard deviation. Boom, there we go. Okay, and in this situation, I'm picturing a normal curve. Here's that lowest 1%. And I know that up here, the minimum is 3.95. So x equals 3.95. Okay, so here I know that my situation is saying, well, what would our mean have to be with our standard deviation staying the same so that only 1% are too small to fit? So here I know that I can figure out what the z-score is that goes with this proportion below. So I know that I'm looking at an area below of 0.01. So I can do inverse norm, 0.01, 0, 1. So here again, proportion below, mean, standard deviation. So when I plug that in, pump it out, I get negative 2.3263. Okay, so now I need to figure out, well, what does that missing mean? We've had a couple of these today. So I'm going back to x equals the mean plus the z-score times the standard deviation. 3.95 is the observation. That's the minimum diameter of the cup lid. The mean, I don't know it. My z-score, I solve for it, negative 2.3263, and a standard deviation of 0.02. So algebra problem from this point on. So 3.95 equals the mean minus the product here is 0.0465. Okay, add the 0.0465 to both sides, and I get a mean of about 3.9965 inches. So if we keep the standard deviation the same, right, the mean has to be altered, has to be a little bit higher, 3.9965, so that only 1% are too small to fit with our constraint given above right here. Okay, for B, if the mean stays at 3.98, what would our new standard deviation have to be if we want only 1% of lids that are too small to fit? So here, the visualization looks the same, lower 1%. Here the x value is 3.95, that's my observation. My situation is normal. I do know my mean. It's staying put at 3.95, but I'm solving for my unknown standard deviation. Since my areas here and here match, that z-score that I would have had to solve for is the same. So negative 2.3263. Okay, so back to x equals the mean plus the z-score times the standard deviation. So 3.95 equals, my mean is 3.98 plus my z-score, negative 2.3263, and a standard deviation right there. Okay, so again, algebra problem. Take away the 3.98. So I get a negative 0.03 equals negative 2.3263 times our standard deviation. Divide away the negative 2.3263 from each side. And I get a standard deviation of about 0.0129 inches. Okay, so if our mean stayed the same at 3.98 inches, we can see that our standard deviation would have to be reduced slightly to 0.0129 so that only 1% of lids are too small to fit. Okay, one more problem. Quebec is the only province in Canada where the one official language is French. According to a recent census, 79.7% of Quebec residents identify French as their mother tongue. You select an SRS of 165 Quebec residents. Okay, so right here, there, that's our P. Right here, that's our sample size, that's our N. So our mean is 0.797. I'm just writing it as a decimal. Okay, if you wrote it as a percent, again, no problem. Standard deviation. So P, 0.797 Q is the complement of P, so 0.203. Standard deviation, sorry, not standard deviation, sample size, 165. So here I'm looking at square root PQ over N. So here I'm going to get about 0.0313 for my standard deviation. So we expect a mean of 79.7% of Quebec residents who speak French, who think of French as their mother tongue, with a standard deviation of 3.13%. Okay, check the three assumptions. So first, randomization. Okay, so if I skim through, does it say anything about it being random? Oh, yes, it does. It says SRS. Okay, 10% condition. So would we say that 165 Quebec residents is less than 10% of all Quebec residents? Well, yes, that would make sense. So 165 residents is substantially less than 10% of all Quebec residents. Right? So 10% condition, we have met it. Okay, lastly, success failure. Okay, so we want it big enough, but not too big. So here we're checking to make sure that we have enough successes and that we have enough failures. So we're looking at our sample size of 165 multiplied by our probability of success, so 0.797, and we get 131.505. Great, more than enough. We definitely have enough successes, definitely more than 10. Okay, here we're doing 165 times 0.203, right? That's our Q, complement of success, and we get 33.495. Okay, so absolutely, right? We see that we are greater than or equal to 10. Check. That third criteria is met. Normal model is appropriate. All right, and then once we've decided that, we push forward one last part. So, if it is appropriate, which it is, calculate the probability that less than 72% of the people in the sample identify French as their mother tongue. Does this seem unusual? Why or why not? Okay, so if I flesh it out, here's my normal curve. Here is my mean, right smack in the middle, 0.797. So we're saying, okay, we're coming up with a 0.72. So somewhere around here. We're saying 0.72. So is it unusual to see 72% of Quebec residents or less that identify French as their mother tongue? So here, negative infinity. And then here I would do my placeholder for negative infinity. So anything that's in the 999s, right? Anything that's like really big, right? It's a placeholder for infinity. So I could use really anything that's really large, really large, or really small, depending on which one I'm trying to substitute in for. So over here, I would say typically negative 999 is what I use. I could go negative 9,999. I could do negative 1 million, right? I just need something that is dramatically in that lower tail as a placeholder for negative infinity. All right, so here we go. Now we're going to take it to normal CDF. I'm using negative 999 as my placeholder. Up to 0.72, lower to upper boundary. My mean is 0.797. My standard deviation, 0.0313. So let's crunch that together. Last problem. So normal CDF, negative 999, comma, 0.72, comma, 0.797, comma, 0.0313. There we go. So we get 0.0069, which would be about 0.69%. So less than 1%. So does that seem unusual? Absolutely. Yes, unusual. Okay, what's our threshold for unusual right now? We're saying it's unusual if less than 5%. So we're saying, yes, it's unusual because less than 1% of samples of this same size, of size 165, identify French as their mother tongue. All right, good review for today. Hope you guys are feeling pretty solid. Hopefully you've had sufficient practice and you are ready for your quiz. Have a wonderful rest of your day. Keep asking questions.